Okay, hello everybody. Uh, this is your sludge digestion module. Uh, as I mentioned last lecture, I'm going to start combining lecture material from both the Ragsdale Manual as well as the New Mexico Environment Department Wastewater Operator Review Manual or Study Guide. The idea here is that I want to make sure that I don't let anything slip through the cracks and that y'all are prepared and see all the material you need to for your certification exams. So this will be the first chapter where I combine both manuals or publications. I will likely go back through chapters 1 through 4 and pick up any material that I left out from the Environment Department Study Guide. So again, the whole point here is to really help you with your study efforts, vice just trying to go through the motions. Okay. So a few administrative notes. As I mentioned, we're going to contain material moving forward from both the Ragsdale Manual and the Environment Department Study Guide. In order to guide you so you can look things up so you know where material is coming from, I'm going to list the source, the chapter and page number on each bullet point or on each slide if it comes from one source in its entirety. And again, I'm going to help do this to help you focus and look at materials for each source. The way I'm going to recommend you use the manuals are to read the Ragsdale manual as a text to understand the concept of each process. And we're going to give you test questions from this source, both in our quizzes, our final exam, which is going to be a sample certification exam, and you are going to see a number of questions directly out of the Ragsdale manual on your certification exam. Uh, and so Fred Ragsdale wrote his manual in such a manner that it is really easy to read. It contains all the highlights. So that'd be the first thing that I'd tell you to read. And after doing that, watch the lecture and then go back and read the Environment Department Study Manual. And I'll call the Ragsdale Manual RM in my citations and the New Mexico Environment Department Study Manual or Study Guide NMED in my citations. But you're going to find NMED is going to give you a detailed information on each process. And after chatting with Nathan in our second class about that, I said, you know what? They are going to use that for Trivial Pursuit and for notes and what have you. But the idea here is I think you're going to find that as we go through this lecture in particular and following ones, that a lot of the material in the Environment Department Study Guide is in the Ragsdale Manual, but there is some stuff in the Environment Department that Fred Ragsdale didn't capture. But again, his was a review course manual designed to get you the biggest return on your study time and on your value. Okay, so that's how I'm going to recommend you study. I'm going to include, as I mentioned, material from both sources in your weekly quizzes or your homework assignments. They're really homework assignments, but I patterned them after quizzes because I want you guys to get used to taking the certification exam. It's a computer-based exam, and I think this will just help you get used to the format. I'm also working on 4 sample exams, levels 1, 2, 3, and 4, that I'm going to publish before July 4th or on the weekend of July 4th so that you can start looking through them and practicing. Those are going to be your final exams. You are welcome to take all 4 if you like. You are welcome to take the only one that you're going to be testing for. Whatever you think is going to help you. If you are testing for level 2, I'd say take the level 1 and level 2 exams. I wouldn't bother with the level 3 and level 4 because you're going to cloud yourself up. So I don't want you to focus. If you're taking a level 3 exam, uh, levels 1 and 2 should be very straightforward for you. So I'd take them and then I would go to level 3 and then perhaps take a look at level 4, but don't confuse yourself. Don't feel, for example, if you're trying to take a level 1 exam, that you got to take all 4 levels. It's just not necessary. And like I said, it'll probably confuse you more than help you. But if you're taking one of the higher levels, go ahead and take, 1, 2, 3, 4, whatever you want to, okay? I need you to keep working on the material. I want you to pass the exams, and you can do that. But the idea is like any exam, professional series exam, which is what these are, you got to start early and you got to stay consistent. You got to hit the review manuals. You got to look at the sample questions. Um, and in addition, particularly the Ragsdale manual end of chapter questions. Strongly recommend you go through those as well. You'll notice that I'll repeat some of them, but not all of them. This is going to give you additional study material. And as I've mentioned earlier, in the Ragsdale manual, the back of each chapter, the tail end of each chapter, they'll have basic study questions and basic sample exam questions. Those are what folks looking at level 1 and level 2 certification exams should be studying, looking at, and trying to work through. The advanced stuff, the advanced study questions, the advanced sample test questions, that's what people going for level 3 and level 4 should focus on, okay? So I want to make that clear. By all means, don't ignore those questions. You are going to see some of those on your certification exams. Not all of them, but the idea is they're very similar in scope and content that show up on the exams, okay? So sludge digestion. We talked a little bit about this. So we went over solids handling last week or last lecture. So let's catch ourselves up. We started with preliminary or pre-treatment, if you will, and that was basically removing the large debris from our incoming influent, our wastewater stream coming from the collection system and then coming into the plant. And we got rid of wipes, rags, branches, debris, any of that stuff. We're looking to get rid of bigger stuff that could harm our equipment or interfere with our process. In addition to that, we went through some grit chamber work where we tried to settle out sediment and sand or even coffee grounds. We let those settle out, and using air flotation, we allowed the separation of organic material, suspended material, to float up to the top of that influent, and for the heavier inorganic sand or pebbles to settle out, settle down, where we basically send to a grit washer to remove any organic material and to remove any potential for any odor causing organic material to stay on that grit. And then we landfill that. And the influent after grit removal and after preliminary treatment heads to the primary clarifier. And in that primary clarifier, as we mentioned, we're letting gravity do the work for us. The larger settlable solids or suspended solids are going to come down as we slow down the flow of wastewater, again, from 2 foot per second in the collection system to 1 foot per second in the preliminary treatment and grit washing. Now we're at about 0.05 to 0.03 foot per second. We're really slowing the flows down in the primary clarifier, which allows us to have that suspended organic material to settle out and form our sludge blanket. And our sludge blanket is just the suspended material settling out at the bottom of the clarifier. Okay, and we also have some scum floating at the top, particularly like fats, oils, greases coming in. And recall that in the primary clarifier, we have a scum skimmer up on top of the water surface, and that's going to scrape and guide that scum into our scum box. And we're going to take that away so that we don't send it off to future treatment. And that sludge forming at the bottom, that sludge blanket forming at the bottom of our clarifier, we're using a rake apparatus to send that to the center of our primary clarifier, and we're going to waste some of that sludge. Well, that wasted sludge from the primary clarifier is going to go to the digester. Okay. In addition, when we look at the secondary clarifier, that secondary sludge, some of that waste activated sludge, we're going to recirculate like 2% of it, but the majority of it's going to go to waste, which is the digester. Okay. So the idea with the digester, we talked about last go round, talked about solids handling. The digesters are a biological method to thicken our sludge. what we're basically doing is we're using these microbes, these bajillion microbes, if you will. That's the scientific term, bajillion microbes. And those microbes are digesting the sludge. And by digesting the sludge, they are helping separate the solid particles of the sludge from the water. They're removing that trapped water, which means we're increasing our solids concentrations. Okay. So what sludge digestion is doing, it's stabilizing that volatile organic material. Okay, we're bringing it down into sludge, and we're increasing the sludge solids concentration. And the organic content from that sludge that we're digesting is 60 to 65% of the total solids. That's organic. That's what our bugs are going to feed on in our process, okay? We're also releasing the water, that bound water. So if you think about it, you can look at it as just like a mud slurry, if you will, and the microbes are separating that water from that mud or that sludge by munching away at that organic material. Okay. And the end goal here is we're minimizing what we're sending to the landfill or composting. We're increasing the solids concentration of our sludge, getting rid of the water, so we got less volume to deal with. Okay, less weight to deal with. Okay, now we're going to find that there are two types of digestion that we're going to deal with as wastewater operators. One is anaerobic, and that is digestion in the absence or with extremely low oxygen content or an absence of oxygen content. And we found in our initial lecture, we talked about an anaerobic process. It's going to produce carbon dioxide, methane, and hydrogen sulfide. Okay. And those, the methane, the hydrogen sulfide, the methane in particular is flammable. So there are some risks going anaerobic digestion with this, okay? We also have aerobic digestion. And aerobic digestion, we are only producing carbon dioxide. The bugs are respiring carbon dioxide. They're not giving off hydrogen sulfide or methane, okay? And aerobic digestion, the bugs love having the oxygen around. That's how they're metabolizing this waste. So that's aerobic digestion, okay? So you really want to be clear on the two types of digestion. The fact that anaerobic is in the absence of oxygen, anaerobic is in the abundance of oxygen, okay? And here's the citations. RM is Ragsdale Manual, Chapter 5, Page 1. That's where this material is located if you want to go back and read the manual, which I highly recommend, okay? Now, what's an anaerobic digester, okay? So an anaerobic digester, it's a Mondo big tank, but it's sealed. And the idea is that seal is not going to allow oxygen in. So we're keeping the environment oxygen deficient on purpose, okay? And we use these anaerobic digesters, or these circular tanks with a cap on top, a cover on top. And inside them, we got these billions of bacteria. They're breaking down the organic waste without using oxygen. And the idea is we're cleaning the water. We're getting rid of that organic stuff, separating the sludge from what's called a supernatant, which is a wastewater liquid mainly that's going to rise to the top of the tank. And we're going to decant it or get rid of it in this digester. So the process is going to clean the water, but here's something else that it does. It creates biogas. Hydrogen sulfide and methane. We are extremely interested, if we're using an anaerobic digester, in the methane for a couple of reasons. One, we can harness that methane and we can run a generator off of it. It's called cogeneration. And we can power the equipment in the wastewater plant with this methane gas. We're going to burn it off anyway. As a safety feature, we do have flame arresters. We're going to, burn that methane off. Well, if we're going to burn it off, we might as well get something out of it. We might as well get a return. And that's what some plants do. They'll take this methane gas from the anaerobic digester, and they'll use it to power a generator to produce electricity and power the wastewater plant. Okay, so it's pretty slick, innovative method here, and I don't want you to think this is gathering speed across the nation, but it's been around for a while. It's just lately with the climate change stuff, the wanting to avoid greenhouse gas emissions, what have you. This has really taken on a life of its own and had a renewed effort for plants across the nation to implement this. It's a great technology, and it is, as weird as it sounds, this is a green or clean technology because we're avoiding, even though it's wastewater, we're avoiding the discharge or the emission of greenhouse gases. Okay. So we're still sticking with anaerobic digestion, okay? Lack of oxygen in this sealed tank. We're going to talk a little bit of biochemistry and design for these digesters, okay? And if you have not taken Professor Gomez's microbiology course, he talks quite a bit about this. So he doesn't just deal with water or wastewater, he talks about a lot of the microbiology. I don't remember what number it is in the water series, but it's well worth considering taking if you're really into this stuff, okay? So for an anaerobic lack of oxygen digestion setup, we need an absolute absence of dissolved oxygen. The wastewater's got to be void of dissolved oxygen for this to really function well. We have these acid formers, okay? These acid formers, these microbes, they're going to convert complex organics into organic acids. Okay, so they're going to form acids, if you will. And we've got these fermenters out there, these little bugs, they're going to produce methane. They're going to take these organic acids we formed and they're going to convert them into methane gas. So we start out with these complex organics, whether they're sugars, proteins, carbs, whatever coming in, and the acid formers, these bugs or these microbes turn those materials into organic acids, and then these fermenters that are in the setup as well, the microbes there, they'll convert these inorganic acids we formed into methane gas. We want to run this process, anaerobic digestion, for the methane fermenters to function. We need to look at a pH between 7 to 7.2. Okay, that's what we want to operate the anaerobic digestion process at. Okay, for a volatile acid over alkalinity ratio, we want to operate below 0.4. So the ratio of volatile acids to alkalinity, okay, got to go below 0.4 for this to work. Okay, and what we're going to find a little later is the volatile acid to alkalinity ratio being below 0.4 and the pH varying outside of 7 to 7.2. If these two vary, these are symptoms that we're going to have something called a digester upset that we'll talk about. The volatile acid or alkalinity ratio, this is the quickest way and the precursor. This is the first symptom you're going to see. The pH is a follow-on symptom of a digester upset, but we'll talk about that in a couple of slides. Okay. Now the solids loading rate, we want to plan for this process to take place of anaerobic digestion. We want 0.15 to 0.35 pounds per day per cubic foot. Okay, so we're dealing with cubic feet vice gallons here. Okay, so that's what our solids coming into our digester, the concentration on a daily basis must be at for this anaerobic digestion to work well. Okay, let's take a little bit of a step back and let's talk about the bacterial groups we're dealing with. We've got three very distinct and temperature sensitive groups of anaerobic, again without oxygen. They exist and they're needed for this process. We've got these psychrophilic microbes, and these microbes, they can contribute to reactions, these biochemical reactions of converting complex organics to organic acids, then into methane gas. They can do that in cold environments, okay? And they function where the other organisms don't live. Okay, and we'll give you an example of where we'll find these, but these are psychrophilic microbes. You can think of these as cold-loving microbes. They like to work in lower temperatures. Then we have these mesophilic organisms. These mesos, middle, is the prefix for meso. That's the meaning. Meso means middle. So middle loving organisms, they're going to operate best in moderate temperatures. You can think of this as the Goldilocks, not too hot, not too cold, and they're in an optimum growth range between 20 to 45 degrees Celsius, which is pretty much a spring, summer ambient temperature day. Okay, this is so cold loving organisms, middle temperature loving organisms. Then we got these thermophilic organisms. They love higher temperatures between 50 to 60 degrees Celsius. Okay. I like giving you guys these rules of thumbs, and Fred Ragdale was all over them. So a rule of thumb here, or a heuristic as it's often called. I knew one person that was very offended by the term rule of thumb. Uh, and so if you are not meaning to offend you, you'd have to look it up to find out why they were offended. But the stability rule is for an anaerobic digester, you don't want to let the temperature change more than 1 degree Fahrenheit per day. Okay, if you let it change more than one degree Fahrenheit per day, you're going to have issues. You're going to cause a digester upset that we'll talk about later. That's the rule of thumb. It's a real easy number to remember, 1 degree Fahrenheit per day. Again, for anaerobic digester temperature movement. Okay, so if you exceed the daily limits that we talked about here, it can cause immediate foaming and process upsets in your anaerobic digester. And foaming is just a visual. Your digester's upset when you see foaming in it. Okay, or you get foam out of the supernatant when you decant it. And you're going to find that I'm going to compare you having an upset stomach with a digester upset. And it'll make sense as we go along, but keep that in mind, okay? So for the psychrophilic bacteria, the cold-loving microbes, again, in degrees Fahrenheit, 50 to 68 degrees Fahrenheit. We're switching from Celsius to Fahrenheit. These are in what are called Imhoff tank digesters and also in septic tanks. Okay, so these are very slow-moving processes that are taking place in an Imhoff digester or septic tank. It's a really inefficient microbe in how they have these biochemical processes take place. So if we were to use psychrophilic bacteria, it's going to take us 2 to 3 months to 4 months to stabilize that sludge. Okay, it's not going to produce a lot of methane, but it is going to produce high level of hydrogen sulfide. Okay, and thing is, we're going to have odor problems occurring because of a lack of gas collection. It's not efficient to collect all, the gas that it's produced because it's such a low level. So you're going to see these, like I said, in the Imhoff digesters as well as your septic tanks, more commonly in your septic tanks, because I think that's what we're all familiar with. So when you go to a rural residence and you see somebody cleaning out their septic tank or getting it pumped out, and they pop that cover off, that you just get that huge whiff of hydrogen sulfide. It's very odoriferous or foul smelling. Okay, so these are psychrophilic bacteria. That's where you'll see them. You really won't see them in a municipal wastewater treatment plant. Okay. And the mesophilic bacteria, though, those microbes are going to operate between 68 to 113 degrees Fahrenheit. But here's where we're going to thrive. We're going to get the best use of these microbes between 85 to 100 degrees Fahrenheit. And most of the municipal digesters, they're going to run towards the higher end of this range between 95 to 98 degrees Fahrenheit. And in this case, it's going to take 25 to 30 days, close to a month, to get that standard sludge digested. Okay. It's not going to give you much of a yield of gas per pound of the volatile organics, 8 to 12 cubic feet. Okay. And of that 8 to 12 cubic feet per pound of organics, the composition is going to run 65 to 75 to 70% methane, and the remaining amount, 30 to 35% is carbon dioxide. Here's the thing though. the energy level of that gas produced is 500 to 800 British thermal units, or BTUs per cubic foot. So it is an energy rich gas that's coming off there, okay? And we're going to switch now to the thermophilic bacteria. Again, these are heat-loving microbes. Here's the temperature range they like to operate in, 120 to 135. Most of them are heated. We do heat these digesters to keep that range, that temperature range in effect, okay? And it's 124 to 126. So we're going to view a couple of schematics a little later on where we're going to see how we heat these digesters, okay? It's kind of interesting. So there's a trade-off here. So we can produce higher methane percentages than we did in using the mesophilic bacteria. But here's the thing. We've got to heat the digester to this range. So we're pouring energy into heating, and that energy could have been used for cogeneration. Okay, so this high heating demand, we're really not going to get a lot of use out of the methane as far as cogeneration. Okay, but here's the big benefit to these thermophilic bugs. We're going to complete digestion using these bugs and heating up that digester in 5 to 12 days. And we can shrink what we would need for an anaerobic digester using like a mesophilic bacteria. We can shrink that tank volume by 50%, okay? And it's an extremely efficient digestion, but we're just not getting the gases that we need, okay, for cogeneration. These guys, though, these microbes, you can shock them very quickly with rapid temperature changes by putting too much sludge in and feeding the digester too much sludge. So they're kind of delicate. They think of them as having delicate digestive tracts. So you can shock them if you misoperate. You can shock them fairly quickly, and you can cause a digester upset. You can cause an upset stomach, if you will, to your wastewater plant. Okay, so there's trade-offs. So we've talked about the psychophilic. Okay, that's the septic tank stuff, and the Imhoff digester. We're really not going to see it in our wastewater plants. We've talked about mesophilic digesters, and those are great for cogeneration if you can force that digestion, but it's a long time to digest the sludge. And then we can look at thermophilic, which we have to pour energy into, but it's an extremely efficient digestive process. But again, it is a delicate balance here, okay? We can cause a digester upset with this, okay? A couple of other things with the thermophilic bacteria or microbes. We can have what's called a caking hazard. And what that means is sludge will literally bake onto pipelines that are bringing the sludge in when the heat exchangers that we're going to look at in a minute get to 130 degrees Fahrenheit. We're caking up our pipelines, okay? We're clogging ourselves up here when we start heating at the higher end of that range we talked about. We can also have, if that sludge bakes on and clogs, it can clog the heat exchangers, and it can insulate the heating coils. So we're basically causing ourselves problems by allowing these temperatures to go near the higher end of the range at 130 degrees Fahrenheit. We get the caking hazard where the sludge is going to bake onto the pipelines or the heat exchangers and coils. And when that happens, we're not going to get much of a heat exchange. So the remainder of the sludge that we're trying to keep at a certain temperature range, it's going to go away from that temperature. It's probably going to get cooler towards the outer edges or the further away you get from the heat exchanger, okay? Again, I'm going to repeat this with anaerobic digesters. Here's rules or guidelines for our operational temperatures. This is where we want to keep them, okay? We don't want to adjust our anaerobic digester greater than 1 degree Fahrenheit per day. It's a slow moving heating and cooling adjustment, okay? It sounds strange, but you go above this plus or minus 1, you go to like 1.5 or 2, you're going to cause yourselves a mess, okay? And again, the psychrophilic bacteria or microbes, they operate in the cold. Here's the temperature range, 50 to 68 degrees Fahrenheit. But again, the digestion period, 2 to 4 months, long time. That's why they're great in septic tanks, but we don't use them in a municipal wastewater treatment plant. Okay, mesophilics, moderate operation, or they operate moderately in this temperature range, 68 to 113 degrees. Optimums here. And again, it's about a month-long digestion for your sludge, but it's going to give you a lot of gas. It's going to give you methane that you can use for a cogeneration facility. So what you will see some plants do is they'll have a smaller digester, a mesophilic digester, where they'll send sludge there just to produce methane gas for a cogeneration operation, where they'll take that methane gas and run a generator. It'll be a smaller digester, but they'll take their time and they'll separate it from the thermophilic digester, anaerobic digester. So these are going to run pretty hot, and they're going to run or digest those complex organics in 5 to 12 days. Here's the thing though, they're not going to produce anywhere near the methane you're going to need for cogeneration. Plus, it's going to take energy to keep these microbes comfortable in the anaerobic digester, okay? But a very efficient digestive process to concentrate our solids, okay? And remember, sludge is going to bake onto coils, heating coils and pipelines above 130 degrees Fahrenheit. That's called a pipe caking hazard, okay? So the next set of slides, we're going to look at some schematics for the anaerobic digester and their components. I put a schematic in there from the NMED study guide, but I got to tell you, I couldn't read it very well. So I also said, you know what? Let me show it to you. If you can read it well, fantastic. I could not. So because of that, I also put in on the next couple of slides schematics from the Ragsdale manual, which I think you can see and you can read. And I blew them up for the entire slide, okay? We're going to cover the functions of the components and discuss some safety features and troubleshooting, okay? But remember, okay, we're talking about an anaerobic digester, no oxygen, okay? Let's not say extremely, let's say with no oxygen, a little easier to see, okay? No oxygen. And remember that process is going to produce methane, CH4, hydrogen sulfide, and there's the chemical formula H2S, and carbon dioxide. Remember, methane is flammable, okay? But very flammable. Okay. Here is what I was talking about with respect to the NMED study guide, their schematic. This is a technically correct schematic, but even with my glasses on, I could not read all the notes here and all the labels, okay? So it's not a clear or helpful figure to me. If you have better eyesight than myself, by all means, take a look at it. The next couple of slides are from Ragsdale, and I'm going to make a point when I get back to work. I'm going to walk down the hall. I'm going to talk to the utility operator certification program manager, and I'm going to say, you might want to relook and rethink that diagram because that's hard to read. And to me, it wasn't very helpful. But this is a fixed cover digester, and this is a floating cover. This is a primary digester, the fixed cover, and the floating digester, that's the secondary digester. And we'll take a look at a little better diagram. Here you go. So to me, it's not as technically savvy. It's more of a cartoonish drawing than the previous schematic, but it's easier to read. So refer to this if you want to print it out, or if you want to open up the Ragsdale manual, get to that chapter when we start talking components, please do so. But let's look at the primary digester, okay? So as I told you, we're feeding, that's what we call feeding the digester. We're pumping in primary sludge, which is what we're collecting from the primary clarifier. And although we haven't talked about secondary treatment yet, we're also wasting, is what it's called, wasting secondary sludge. So these are both considered wasting sludge. We're going to send the sludge from the primary clarifier and secondary clarifier, okay? We're going to send it into the primary stage, okay? And what's going to happen is we'll see a little bit more of another close-up view here. We're going to collect gases here, okay? And we've got a gas mixing system where we are basically mixing the gases, compressing it, and we can send it to a flame arrestor and burn it off. Okay, and what happens here is we talked about converting the complex organic compounds material coming in with the sludge, the protein, sugars, fats, all that stuff. We're converting this in here to the organic acids. We're also starting to form some methane, and that's where that gas is taking off. And we're collecting it up here, mixing it and arresting it at the top of the digester here. And the sludge, we are pumping the sludge from the primary digester. We're pumping it into the second stage of the anaerobic digester. Again, anaerobic without oxygen. So we're doing that. The sludge is digested, and what's happening is the solids have, or the sludge has let go of this captured water. Okay, so our solids concentration in here is much greater than the sludge we sent from the primary and secondary clarifiers. So we're collecting this digested sludge, which has increased in its solids content. That's the beautiful part about it, okay? We have just saved ourselves a whole lot of money by not having to handle wet sludge. So it sounds silly, but with the volumes we're dealing with, makes a huge difference, okay? And the supernatant, that's basically the freed up water. It's still not clean water. It's nothing you're going to want to drink, but the supernatant, we're going to basically send that off into like an oxidation ditch or a aeration basin before it goes to the secondary clarifier, okay? So that's the supernatant, and we've got a floating tank cover here. That floating tank cover is kind of a, well, it's not kind of, it is a safety feature. So if we're still gathering gases and we don't, and let's say we have some issue with a misoperation, we produce too much gas, well, we want to make sure that cover can kind of float a little bit and not be pressurized to the point where we're going to have an explosive situation. Any gases formed here, again, we're going to have a flame arrestor to burn that off and get rid of those methane gases, okay, and hydrogen sulfide gases. So that's a two-stage anaerobic digester, which is a lot easier to see what's going on than the schematic on the previous page from the Environment Department Study Guide. Okay. And here's the primary digester, a little better look at it. What's happening is when we send sludge in, we're sending it to the center of the digester. The digester is a cylindrical tank, a sealed cylindrical tank that has an inverted cone at the bottom. Okay. And we're doing the same thing we did with the primary clarifier. We are bringing in sludge into the middle so that the flow of the sludge comes out and moves outward. And we've got what are called deflection shells here. They're basically baffles so that we're not spraying sludge all over. It's hitting, losing the energy, and flowing out. Okay. Here's a heat transfer mechanism. Okay. This is we're getting gas and collecting gas in the center here. Okay. But we're also have a heat exchanger here, and that heat exchanger is what's keeping us at our optimum temperature range. But remember, if we misoperate this and we go above 130 degrees Fahrenheit, what's going to happen is this sludge is going to cake onto the heat exchangers here, and the sludge out here, further away from the center of our digester, it's going to cool down. And we're going to probably have that plus or minus 1 degree Fahrenheit exceeded fairly rapidly, and that would be caused by misoperating the temperatures here, okay? And so what's happening here is we have, sorry, I am struggling because I didn't bring my glasses with me, so I'm going to lift up the computer and look a little closer. So what's happening here is we have at different levels of the digester, we have supernatant, or that separated water. We're just going to start collecting it here, and it's eventually going to go to like a launderer or an effluent, okay? An effluent launderer, and we're going to collect that away, but we're collecting this separated water at different levels of the digester, okay? And we are controlling the heat exchange in the middle, flows coming out, and we're collecting gases. And you can't see the valves up here, the flame arresters and safety valves, but there is a photo in the Ragsdale manual that talks about how they work and gives you a photo, okay? So the physical tank components that we looked at for an anaerobic digester, we've got pipelines and valves, and the purpose of those, we are just routing and controlling sludge flow in 2 or 3 different directions. I call it complex, or the NMED manual calls it complex, because that sludge has to flow in a counter direction to our heat exchanger. So as we're bringing the sludge in from the primary and secondary clarifier, it's going to flow up, and the heat exchanger is going to flow basically heating fluid in a counter direction. It's going to flow down while the sludge flows up, so that we're heating up the sludge to get the thermophilic bacteria happy in producing, okay? We've got an inlet line, the sludge feed line. It's where we feed the sludge into the digester, and that's going to get us a thickened raw sludge into the primary stage. And those supernatant tubes off to the side that we talked about, that supernatant, or that cleared liquid, it's going to take that off the top of the water column at different tank depths. Okay, and then we've got a sludge draw-off line that I couldn't read because I didn't have my glasses on, and that's going to take the stabilized, well-digested sludge from the bottom, and that's going to take it to the secondary digester. Okay, and that mixing system up top, the gas mixing system, their mechanical units are gas bubblers. They're going to ensure uniformity. We want a constant mix, because if we are collecting the methane, for example, for cogeneration, we are going to want a constant concentration, so that our flames aren't going to sputter on and off in our arrestor or in a cogeneration setup. Okay, the gas system, it's a safety feature. It's going to, in a very safe manner, collect, handle, and pressurize that methane. Okay, the digester heating system, the counter current flow in the center, that's going to take external heat exchangers to maintain these processing temperatures. So, if you will, we'll have outside the digester, we'll run heating fluid from outside the digester at a constant temperature. It's under a set of controls to heat the sludge to keep it at that good optimum temperature unit. Okay, and that floating cover on the secondary stage, it's going to move up and down based on the fluctuating liquid and gas levels in our secondary digester. Okay, we also have a sampling well, and please go back and take a look. You'll see the sampling well. That's going to let operators take out raw sludge for testing. And what we're looking at for testing is like the mixed liquor suspended solids. We're looking to see what kind of microbes we're pulling, what kind of BOD we have. Pretty interesting stuff. And we will go over that a bit later when we hit the activated sludge chapter, okay? So here is the floating cover, if you will, of the secondary digester. We've got a water seal here, okay? And the digester gas pushes down on this water seal, and the difference between that column, internal column here, and the outer column of water, that's the inches of water pressure taking us, or required to keep that cap, or that floating handle, or that floating cover on there, okay? And right here up on top, okay, components 13, 14, and 15, there's a photo in the Ragsdale manual, and it shows you which in a photo what the pressure relief valve is, the vacuum relief, and the flame arrestor are. Okay, take a look at that, and it's got a boxed identification in the manual as well. And as I told you, what's going to happen with Ragsdale's manual is if he puts something in a box, odds are it's going to show up on your exam. So take a look at that, okay? So here's the supernatant box and tubes we talked about, the drain off line here at the bottom, okay? And, for gas, the gas is going to escape via the gas piping. We have a flame arrestor. We also have a condensate drain. So what'll happen is we're basically this condensate, this collector here is going to gather the gas, but as the gas moves through the collector, there's surfaces there, and if there's any moisture coming out with condensate or moisture coming out with that methane gas, these surfaces are going to capture that moisture, and the condensate's going to collect at the bottom of this apparatus here, this chamber, and we're going to be able to drain the condensate out, okay? So we're going to talk now about gas cover and management on the next slide, okay? So that water seal depth we looked at, we want that at about 8 to 12 inches, okay? That water column, the difference between the internal water column and the outer water column, we want to keep it under 8 inches, okay? That's the max pressure that should be allowed to build up in that, or the operating pressure, pardon me, for that floating cover, okay? We've got the vacuum breaker hazard, and what's going to happen is that vacuum breaker, if we introduced air into the digester with the methane gas, which is explosive, we could have an explosion. So that vacuum breaker hazard, that vacuum breaker is going to make sure we're not letting air in, okay? And that gas that's collected, the methane that's collected, can be piped off, collected. We want it, of course, to be free of the condensate. That's why we have that set of surfaces to collect condensate and send it off to the condensate drain. So we want a moisture-free methane, collect it, and we can use that to heat up our heat exchanger, or as I mentioned, some places are putting in a combustion generator where they're burning that methane gas, using it to power a generator to produce electricity to run their wastewater plant. The city of Santa Fe installed a cogenerating system about 12 years ago, and I know they installed it, but I've never been able to get a response from anybody in Santa Fe to ask them how it's working. So I don't know if it's working well and doing its job or not. And I won't say anything other than that. It's puzzled me that they don't publish data on that and show people in Santa Fe, hey, we spent money and here's our return on it. It's just always puzzled me. We also want to manage that moisture. Like I said, the methane coming off of the digester and being collected can have some moisture on it. And by having those surfaces, those tubes, shells, or even just a chevron separator, which is basically a series of metal chevrons, surfaces that'll force the gas to pass through them and will allow any condensate or any moisture to condense on those surfaces and drip down. Now those condensate traps at the bottom of those surfaces, they got to be drained, and they got to be drained manually every day. That means somebody's got to go out there, open up a valve and drain it out. That's got to happen on a daily basis. If that doesn't happen and you allow that condensate to build up, you're kind of defeating the whole point of gathering that methane, because you're going to have a moist or water mixed with that methane, water vapor mixed with the methane. It's not going to burn very well in a generator or in a flame arrestor. Flame arrestors, we want to clean those safety baffles every 3 months. Big deal here, okay? You should remember this. Big safety feature. If we do not clean those safety baffles every 3 months and we have blockage we could create an explosive environment because we're not burning off that methane. We're releasing that methane or not having a good burn. We're causing ourselves some problems. So every 3 months, that's got to be cleaned out, the safety baffles on the flame arresters. The condensate trap, it's got to be drained manually every single day. And water seal depth, 8 to 12 inches. Maximum system pressure, an 8-inch water column, just like we talked about. Important stuff to remember. Okay. Uh, as far as operators go, again, for an anaerobic digester, we want to feed the digester. We want to send raw sludge or waste sludge from the primary and secondary clarifiers. We're going to send that raw sludge to the digester, the primary digester, at least 2 times per shift at low rates. Let's think about this. We talked about sludge blanket management in the primary clarifier. You remember what we talked about? We basically said we don't want rapid changes to that sludge blanket, because if we have rapid changes to the sludge blanket, we run the risk of sending that sludge back into suspension. We don't want that. So think of sludge blanket management as a slow moving process so that we maintain the sludge blanket in the primary clarifier as well as the secondary clarifier. But we're also doing another thing with that. We are maintaining our feed rate for our digester, for our anaerobic digester. That's why we do this slowly. We're balancing things and we're moving things fairly slowly, but we're going to do this twice per shift. And that's why we sent somebody out there, a junior operator, on that catwalk of the primary clarifier. Remember the sludge judge? They wanted to take a look at the sludge column, at the sludge blanket, to make sure that it was okay to start feeding that sludge to the digester. So that's what we're doing. We're managing the sludge blanket, plus we're also managing the digester. Okay. The supernatant, it can also create a hazard. The supernatant, that cleared up liquid that's got the solids removed from it, it now has a high BOD, a high amount of food, a high allowed, high organic content. It's also got a low dissolved oxygen content. We're going to send that to the plant headworks so that we're going to reprocess it, and we're going to make sure that that BOD feeds our bugs and is treated before we send things out, okay, out to the secondary clarifier, secondary treatment, and what have you. So we're sending high BOD and low dissolved oxygen. Didn't write it down here, but it's also got low dissolved oxygen. We're sending that back to the plant headworks. So that's got to be balanced too, because we could cause ourselves a problem by sending too much organic material or BOD out to the headworks and it being oxygen deficient. Okay, this is what I was alluding to earlier. We can upset our anaerobic digester. Okay, we can upset it with a rapid temperature drop, because then our thermophilic bacteria won't be able to process that primary and secondary sludge in an efficient manner. So that rapid temperature drop is going to cause us problems. Or if we feed too much sludge to it, okay? If we have a high organic overload, okay? So think about it like this. I told you I wanted to compare it to our digestive systems. So if we're eating away, we're having a good weekend, let's say we went camping or to a cold football game, and we go to the snack bar a few too many times and we fill ourselves with organic overload, with hot dogs, with beer, with nachos. That's an organic overload if we overdo it. So we could get an upset stomach. But if you couple that with a rapid drop in the temperature, like on a really cold winter day when you go watch the Broncos, or not the Cowboys, because I guess they're indoors now, but you do that, you could cause yourself an upset stomach. Same thing with the digester here, the anaerobic digester. If you let the temperature drop too quickly or you overload it with food, it's going to upset the digester. Remember I told you those thermophilic microbes, they're pretty doggone sensitive. So we don't want to, we want to make sure everything we do is fairly slow moving and gentle. Okay. Uh, but if we aren't gentle and we either cool it down too quick or give it too much food, feed it too much sludge all at once, the digester is going to get upset. And the remedy for the digester to get rid of the upset is we got to stop feeding it raw as sludge for a day, for 24 hours to let it rest, which means we now have a sludge blanket problem or potential sludge blanket problem in our clarifiers and a solids handling problem. So that's why we want to avoid the upsets. The other thing we can do is we can add lime or calcium carbonate to raise the alkalinity. We can do that. It's like taking an antacid, like we would take a Tums if we have an upset stomach. Okay. Now, an upset. Okay. What is it? It happens when that biological balance inside the tank breaks down. So those helpful bacteria, they get sick, they stop working, they die off, they're hungover basically. Saying, "Oh my gosh, I need some Pepto-Bismol." And what that does, the entire cleaning process, of that sludge, it's either going to stall and slow down significantly, or it's going to fail. You're not going to find that in the manual. I just wanted to explain this in my own words. So that's what's going to happen. We stressed our thermophilic bacteria out too much. They died off, or they got sick, or they just said, you know what, I'm going to take some time off to recover. And they're going to take 24 hours off. They're going to call in sick. But we still got wastewater. We still got sewage coming in. We got to treat. So that's why a digester upset can cause us so many problems. Okay. Why does it happen? We either overfeed it. We're going to dump too much waste in the tank too quickly. It's like eating too many nachos or hot dogs or beer at the Bronco game, or something that's toxic to those microbes, bleach, heavy metals, strong chemicals, something gets dumped into the wastewater collection system and we can't catch it. It hits the digester. This is why pre-treatment for significant industrial users is so important. We want a laundry to make sure they're not dumping bleach. We want a metal plating shop to make sure they're not dumping heavy metals into the sewer or any strong chemicals. Okay, even Bueno chili, like I talked about, if they dumped a bunch of green chili peels and stems and seeds into the wastewater collection system, well, that's all got a chemical called capsaicin. That's what makes the chili hot. You get that into the digester, it's going to kill off some of those microbes. Okay, so toxic chemicals can cause us a problem. Overfeeding, toxic chemicals, temperature swings. We're shocking the microbe. We go beyond that 1 degree Fahrenheit rise or fall per day, and we get our microbes shocked. We get them sick. They don't want to eat. Okay. The other thing is, remember I told you there's acid formers in this process? Well, if those acid formers take off and they like munching away at the organic acids we're producing, we get too much organics in, complex organics, we form too many organic acids all at once, and then the methane formers go off. The acid formers, go off, eat those organic acids like there's no tomorrow. The acid formers eat the organics, form the organic acids like there's no tomorrow, and the methane formers can eat those organic acids. We're going to have an acidic environment form. We're going to go lower than that 7 to 7.2 pH range we want. We're creating an upset stomach, an acid reflux, if you will, in our digester. Okay. So what are some of the signs that you have a digester taking place, or an upset in your digester taking place, in your anaerobic digester? Well, foul odors is one. The tank starts to smell like rotten eggs or hydrogen sulfide. You got an upset, either really starting or taking place. Methane production drops, the biogas drops or stops completely. You got yourself a problem. You got yourself an upset. The pH levels drop. They go below that 7.0 to 7.2. So they're now in the 6, even if it's really severe, the 5.8, 6.2 pH range. That means we're killing off the beneficial bacteria. the acids are just killing them off. And if we have foam, thick, messy foam bubbling up and spilling out of the tank. And I think I put a video in your YouTube or video selection of digester foaming. Okay, if that spills out of the tank, oh yeah, you got yourself a big problem. Okay, so these are just my own words. This is what you can look for. Okay, how do you stop it? How do you fix it? Well, you stop feeding it. Okay, just like if you have an upset stomach or your kid does, you're going to stop feeding your kid or stop eating. At least I hope you do, unless you're at a Vegas all-you-can-eat buffet and you just want to go to town. But you're going to get yourself sick with an upset stomach. But you stop feeding new waste into the digester. You can add chemicals. Remember that lime and that calcium carbonate. And what that's going to do is neutralize the acid, just like a Tums will. Okay, and you can pump in healthy bacteria from another tank, another digester, to restart the system. That's called seeding your digester by doing that. Okay, and so we talked about anaerobic digesters. Remember, anaerobic digesters function with no oxygen. Aerobic digesters, it's wastewater treatment that's going to use oxygen. We want oxygen present, and it's going to say we've got oxygen, we got hungry bacteria, and it's going to chomp away at those organics in that sludge coming in, and it's going to, what I call, shrink the sludge, the sewage sludge, by separating that bound water. It's going to separate the bound water from that sewage or that sludge, and it's going to increase the solids content. So that's an aerobic digester. So you can think of it, if you've ever composted and thrown your organic trash in the backyard or in a compost tumbler or a pile, it's just basically the same thing. It's a big compost pile, but it's a lot more efficient and it's underwater. So that's an aerobic digester. We want oxygen present to do this, okay? So how's an aerobic digester work? Again, just me talking about it. We've got a bunch of fans, these Mondo fans, and they're streaming or pumping air streams and bubbles into the tank. We're adding oxygen, okay? We feed the bacteria. So these bacteria that breathe oxygen, they're happy. They're having a blast. They're having time of their lives, okay? They're eating any leftover organic waste in the sludge we're wasting from primary and secondary clarifiers. They're saying, okay, we got all the oxygen we need. We got food coming in. Let's eat, okay? Now, here's the thing, though. If that food or that incoming waste stream, that incoming sludge that we're wasting from the primary and secondary clarifiers runs out, or it starts to get very low in organic or BOD content, those bacteria are going to look around and they're going to say, we're still hungry. They're actually going to start to eat each other. There's predators in those bacteria population. They're going to start to eat each other to survive. And what's going to happen there is your bacteria or microbe population is going to go down. And that bacterial cannibalism, it's going to also reduce the volume of the solid waste. So it's like the whole life process here, okay? I had a professor in civil engineering once taught wastewater treatment, and he had a little curve out there that showed this perfectly. I'll see if I can find it and post it for you. But he talked about, okay, here's our microbial colony starting out. We're introducing sludge and oxygen and water, and here's what's happening. The population starts climbing, goes almost exponential, but the food dies out, and then the bacteria population stabilizes. Then it starts dipping because of this cannibalism, okay? So that's basically how the aerobic, digester works. Since you guys work for the lab, you guys, the LANL also has a federally owned treatment works. You have your own wastewater, or used to, your own wastewater treatment plant, okay? And one of the senior operators down there, to keep his plant going and keeping the healthy bacteria going, it was an activated sludge plant, he would actually buy 50-pound bags of dog food. And he would start feeding that into the primary clarifier and into his digester because he needed organics to keep his microbial population optimum so he didn't have digester upsets or have issues. So he was introducing, kibble, if you will, for his BOD content for food for the microbes. So, a couple of things to think about. Keep this in mind because we're talking about activated sludge plants and it's going to become pretty important later. The BOD, I mentioned this last time, the BOD or organic material represented by that BOD, that biochemical oxygen demand, the organics coming in, that's the food. That's the food that makes these microbes work. The stuff we test for coming out of the digester, the mixed liquor suspended solids, that represents our microbes. And we have, once again, we'll get into this a little later. I know I keep promising, but we will get to it. We have this thing called, let me get my pen up. Is it going to let me? We have something called a food to microbe ratio. That's an M. Not a great one, but it's an M. So what we do is we calculate the BOD, and that gives us the food, okay, portion of this ratio. And we're going to calculate something called the MLSS, mixed liquor suspended solids. We're going to calculate that a little bit later. Actually, you know what? I have a stylus with me. So let me rewrite it here. Here we go. That's a little easier. Food to microbe, that's going to be represented later on by our MLSS, mixed liquor suspended solid. And we're going to calculate our BOD. And we're going to find that based on what our food to microbe ratio is, we can take a look at the age of the sludge. We can take a look at what we need to adjust in our process to keep our good bacteria going and get rid of our bad bacteria or microbes. So we'll go over this, but I'm kind of foreshadowing what we're going to see in activated sludge processes, okay? Moving on. Again, just my own words. I don't want to confuse you, so I want you to realize we're talking about two separate types of digesters. The anaerobic, no oxygen. The aerobic has oxygen. Okay, the difference of an anaerobic digester from aerobic from an anaerobic. Aerobic's going to use lots of oxygen. Anaerobic, sealed, like we talked about, it's airtight without oxygen. We want no oxygen there. That's the difference. One of the big differences. The speed, the aerobic digester, that's going to chomp away at waste much, much faster than the anaerobic digester. Okay. The smell, aerobic digesters, if they're operating correctly, they're not going to produce a lot of odor. It's very little odor. It's going to smell like you turned over a garden. It's going to be like a wet soil or a moist soil smell. An earthy smell is what a lot of people call it. That's aerobic. Okay, I'm not here to tell you that aerobic upsets don't happen or aerobic digesters don't get upsets. They do. Thing is, you got to address those a lot quicker because there's no gas capture system there. That's an open tank. And if you have that upset happening and hydrogen sulfide's produced and there are homes or businesses or even highways nearby, you are going to hear about it very quick. And basically with respect to that, you'll dose it with calcium carbonate, lime. I've also seen people dose it with freeze-dried microbes that are gathered and freeze-dried, and they're predators to go after the bacteria that produce the enzymes that are creating hydrogen sulfide gas. So operators, when they get an upset in an aerobic digester, oh my Lord, you wouldn't be amazed at how quick they move because they know they're about to hear it from all sorts of people. Okay, byproducts. Okay. Byproducts, the aerobic digester does not produce methane gas for green energy. The only gas that's produced by an aerobic digester is is carbon dioxide. That's the only gas produced by an aerobic digester, okay? So those are just kind of some of my observations. And we'll have a few more of them, then we'll go back to the manuals, okay? So why would a wastewater treatment plant use an aerobic digester instead of an anaerobic digester? I told you we can gather methane from an anaerobic digester and run our whole plant. Aren't we going to save water? I'm sorry, aren't we going to save, a little distracted here, aren't we going to save money? Well, yes and no. We're going to create electricity, which will save us money, but in the long run, the aerobic digester, that equipment's a lot simpler to operate and a lot cheaper to build. So we're actually going to save money by using an aerobic digester. Since we don't produce explosive gases, it's a lot safer to operate. Pardon me. And the bacteria we're going to use, we're going to learn a little bit more of them about in the lagoons chapter, in the activated sludge chapter. But the bacteria, although we can have upsets, it's rare because those bacteria and microbes, they're pretty hardy. They're pretty healthy and they can withstand temperature range shifts and all sorts of things. But you're never going to see, or you're not going to see the level of upsets you could see or cause yourself as you would in an anaerobic digester. So these are some of the reasons we would look to use an aerobic vice anaerobic digester, okay? Okay. There was not a schematic in either the NMED manual or in the Ragsdale manual for an aerobic digester, okay? So this is the simplest one I could find on the web. It had a bunch of equations and relationships on there, but I cut those out. That was the B portion of the slide. But basically, here's what's happening. We are just basically feeding in sludge. Let me get back to the, here we go. We're feeding in sludge from either primary or secondary clarifiers, okay? We got these air blowers and we're aerating or bubbling air, oxygen into the sludge. And we've got a mixer. We're mixing, slowly mixing this sludge around, okay? And what's happening is as it's aerated, okay, the sludge, it's going to start falling out. The liquid or supernatant's going to come up and we're going to be able to take that off, and the thicker sludge with higher concentrations is going to be pumped from the bottom. Very slow process. Again, slow in, bubbling, mixing, moving, takes a couple of days. Decant the we're going to decant the water out. We're also going to measure the temperature, and we're going to measure the temperature because we also want to keep this within a certain temperature range. The CO2 is going to gather up at the top and just escape. And then the sludge, we're going to send that off to either a thickener or a belt press or a centrifuge, something like that, okay? So that's a schematic of an aerobic digester, okay? An overview, we talked about it some, but we'll talk about it a little bit more. And all of these are from chapter 5, page 6 of Ragsdale. The process type, it's very similar to an extended aeration activated sludge system because we're bubbling air through it. We're aerating it, okay? We're allowing those bacteria to do its job and concentrate solids at the bottom of the digester by freeing up that water that's going to stay at the top of the column. Okay, it operates in what's called the endogenous respiration phase, which means it's taking in oxygen, processing the organics, and expiring carbon dioxide. That's a fancy way for saying this type of respiration, okay? You need to maintain 1 to 2 milligrams per liter constantly, continuously of a dissolved oxygen, and that's what those air bubbles at the bottom are helping us do. That's where we want the dissolved oxygen level for our sludge to take place. We want to go, instead of 7 to 7.2, we want 6.8 to 7.4 of our pH range, and this is going to take about 1 to 1.5 months of continuous aeration to thicken up and digest that sludge, okay? So that's what we're looking at. The components, uh, the digester tank, the aerobic digester tank, it's just a deep concrete or steel tank, cylindrical tank. It's mainly, I've seen concrete. I've not seen steel configurations, but I have seen a lot of concrete. Okay. The aeration system at the bottom, it's just a diffuser. It's like a PVC pipe or something similar, a pipe at the bottom with a bunch of slots or holes. And that's the header. And that's going to allow mixing, and it's also going to allow for oxygen, dissolved oxygen levels to be maintained at that 1 to 2 milligrams per liter. We've got an inlet and outlet line for our sludge. Again, we want a slow moving process. It's controlling the transfer of waste activated sludge from the secondary clarifier or primary sludge from the primary clarifier coming into the digester, and then the outlet lines remove the thickened sludge with the higher solids content. The supernatant tubes, what they're allowing is that clear surface water. After you turn off the air, that surface water is just going to flow out of there, and that's how we're going to separate again that bound water. Okay, and again, there's the what we talked about. Uh, our inlet for our sludge. Here's the diffuser bubbling up air through here, and it's respiring, it's taking in oxygen, the microbes take in oxygen, munch away at the waste, and they respire CO2, that's the gas leaving. The solids are concentrated at the bottom, the sludge that's got an increased solids concentration, we pump that out, that's our final sludge, and then we decant. It's a temperature sensor here, but there should be a decant tube that allows the cleared water to be taken out of the digester. Okay, that's an aerobic digester schematic. Okay, we can also with these digesters, we can use chemicals and add chemicals if we don't have an activated sludge plant. Let's say we've got a solids issue on a smaller plant, or we're managing solids. We're going to utilize chemicals like lime stabilization uh, in order to stabilize the sludge if we don't have these microbes or the equipment to manage this biological process. So it's going to raise the sludge by adding lime or calcium carbonate, going to raise the pH, and that high pH, it's going to destroy the pathogenic organisms in the vectors. Okay, so this is what we would do if we didn't have microbes or digester at our disposal. We're getting rid of the pathogens, and we're basically going to look at either hauling that sludge off, dewatering it, perhaps putting it in a drying bed or what have you. That's what we would do. Okay, this would be for a much smaller plant. We're not going to do that with a large 1 million-gallon or 3 million-gallon a day influent plant. Okay, we talked a little bit about this in the solids management lecture. Okay, we've got drying beds. Okay, the drying beds are just what they sound like. It's just a plot of land. Looking at it from the overhead, okay, and looking at it from the side, it would just be maybe a slope with a little curb here, concrete structure. We would pour the sludge. Let's make it kind of golden. We'd pour the sludge here, and what would happen is we would pour it in these 10 to 12 inch pores. So we would pour out the sludge here about 10 inches to a foot high. Okay. And what's going to happen is two things are going to happen. The evaporation, the water is going to evaporate from the sludge just due to the heat of the sun. So the water is going to evaporate. And we've got a lip here with perhaps like a little drainage slot here. We're going to allow, we'll have like a sand bed here. Okay, that sand bed will take that drainage coming from the sludge, that water, and it's going to drain it off, and then we're probably going to send that back to the headworks. Okay, but these are the two mechanisms that we use in a sludge drying bed: evaporation and gravity drainage onto a sand bed. Okay, here's a rule. You may get asked this. True or false? Would you ever add to that dried sludge? Would you pour another foot layer on top of dried sludge? Would you put another lift of sludge? The answer is no. You would never do that because you've basically just created more of a wet waste stream. Okay. Wanted to make sure you realize that. You don't want to put lifts in. You want to put one layer in, let it dry out, and then you'll have you'll basically have like a bobcat or something like that uh, to put that in a bin for either land application or landfill disposal, likely landfill disposal anymore. Or you can also start a compost pile with that. Okay. Um, but you never want to add wet sludge on top of a layer of dry sludge. Just don't do it. Also, you want to maintain another important point. The compost, if you're going to dispose of it or have a compost heap, you want to maintain that compost at 140 degrees Fahrenheit, okay, for 14 days straight before you can take it off to a landfill. That's a legal requirement, okay? Maintain the compost, that dried sludge, at 140 degrees Fahrenheit for 14 days. That's an important rule of thumb, okay? That's what we have, the material we have for this chapter, chapter 11 in the Environment Department Study Guide, chapter 5 in the Ragsdale Manual. I have a homework assignment for you. It's a quiz format. Again, unlimited attempts. I recommend you go in, you try and do it cold without the manual, without the notes. Do it a couple of times, see how you do. And then if you need to, go back and look at the manual and the notes. And the idea here is I want you to do it a few times because I think that repetition is going to help you learn. And if I were to just say, okay, you got one attempt and here's the correct answers, I don't think you're going to learn as much. So I'm not giving you the correct answers. You got to come up with those on your own. Okay. I have also posted some videos about anaerobic and aerobic digesters. Okay. Let's talk about your exam a little bit, not specifically with respect to digesters, but just in how to approach it. If you're a level 1 examinee for the wastewater systems operator, in general, know what the components are, understand safety topics. Your level 1 is going to be heavy on definitions as well. Okay, be able to explain what something is, what a component is. Understand those safety topics. Understand sampling. Understand basic operator tasks like cleaning out the barminator, the communator, that kind of stuff. Okay, how to use a sludge judge, how you would measure a sludge blanket, that kind of stuff. Okay, understand basic wastewater mathematics. There's a wastewater mathematics chapter in the Ragsdale manual. It's a very clearly explained set of math topics. The stuff for level 1 is pretty basic. Volumes, surface areas, flow rates. I'll start posting some sample problems in a separate module because I don't want you to try and swallow it all at once, okay? Level 2, in general, you got to take the components you learned about and were tested on with level 1, and you got to know what they do as a level 2. You got to know the purpose of the daily tasks. You still got to know safety topics. You always got to know that. Your wastewater math is going to be a little more complex. Flow rates, detention times, that kind of stuff. The level 2 exam is heavy on the ponds and lagoons chapter. I think it's called lagoons in Ragsdale. Very heavy on that topic. Okay. Level 3 examinees know safety topics well. Focus on the activated sludge process, on rules, regulations, and laws. There is a chapter on rules, regulations, and laws in the Environment Department Study Guide. Read that over. This is the exam that a lot of people called math from hell, because you got to know the concepts, but you got to be able to run a bunch of calculations with the material and data you're given in a question, and then explain what it means. Okay. You've also got to troubleshoot systems. They'll give you symptoms of a system. You've got to know what it means. You got to know how the system works and what to troubleshoot to fix a problem. Okay. That's a level 3. I thought the level 3 was a bit more difficult than the level 4. The level 4, and maybe it was because I started working a lot more with level 4 stuff at the time, but still got to know safety topics for every exam. You definitely got to understand the activated sludge process and the rules, regulations. A lot of math again, a lot of troubleshooting. Here's another thing that gets added on. You got to be able to read operational logs. Pick out what's relevant. They're going to give you a paragraph. They're going to give you a bunch of data and then ask you 3 or 4 questions on that data. You got to know what to pick out for the log they give you and explain it or troubleshoot it, okay? For level 3 and level 4, you got to understand chlorine disinfection and complete dosing problems. If you're given unit costs of chemicals or electrical costs for pumps, then you got to be able to put together a budget. What's it going to cost to run a pump for a month with these system characteristics, with this flow rate, with this head, with this friction loss? Here's the cost of a kilowatt per hour of electricity. Here's how often it's going to run. That's something you should be able to run through fairly quickly. Sounds intimidating? It's really not that bad once you read through, I think, the Ragsdale Manual on math, but you're going to see this. Level 4, a lot of math in level 4 too, okay? So there's all that. So I wanted to put that out. So we're not in person, so obviously you can't ask questions, you can't make comments or give me feedback. What you can do is, if you need to talk to me for anything or chat about anything, I can arrange for a call or a Teams meeting. Just let me know. Here's my text. Here's my cell number. I have international access right now. Shoot me a text. Let me know when you want to talk. I may propose a different time so it's reasonable for both of us, because there's a 13-hour time difference where I'm at and where you're at. Okay. I'm putting up a question and answer discussion on Canvas for each module. I think, Manny, you already posted something as an observation. Thank you. That was great. Use it to interact with me and your classmates on stuff you may not understand. Ask each other questions, okay? Work together if you like. I like it when you try and do things on your own once or twice, but don't get fixed into that. You got to be the Lone Ranger. Work with people, okay? Study with people, okay? Please, if you have not completed the week 1 or week 2 feedback quiz, that's just a question. What did you learn? What can you do? What can we do better? Please complete it. You do get graded on that for this class. And if you haven't completed the assignments, it looks like almost everybody has, but if you're falling a little behind, please don't fall behind. Please do your best to try and keep up, okay? So that concludes the digestion chapter, the digester chapter, sludge digester and digestion chapter. I hope you got something out of it. Please take a moment, if you can, watch the YouTube videos. I'm trying to get you a good cross-section of topics out there that I hope will help you understand what's going on. Okay, I'll look back on the foaming of a digester, and if I don't have foaming of a digester up there as a video, I'll add one, okay? Because I think it's important to see that. It's kind of cool. A little gross, but kind of cool. And next, we'll start on the next chapter. I'm probably going to publish 2 over the weekend, and then next week I'll publish 2. I don't want to overwhelm you. It's not my intention to overwhelm you, but I'm overseas. I'm on vacation, but I want to make sure you have the material you need. So it's a balance. I don't want to overwhelm you with a bunch of material, but I also don't want to slow you down. If you're planning on taking the exam in August or September, I want to make sure you got study time. So for the next couple of weeks, try and work at your own pace, or not try, do work at your own pace. If you do that, I'm confident by the time we start having live classes again, you guys are really going to be caught up. And if you're not, don't sweat it. We have some leeway built into the schedule where we're going to be okay. At the rate we're going now, we're going to be probably chapter 10 or 11 by the time I get back. And don't let it overwhelm you though. If I'm going too fast, say so. Shoot me a text, shoot me an email, put it in the discussion board. It's really all okay. That's all I have for you guys for this section, for this module. I am going to post the recording and it's going to be on YouTube. And for somebody that asked, where's the past recordings? I emailed y'all directions how to get to past recordings, the Teams recordings. And I think for chapter 4, I didn't publish the link on Canvas for the YouTube link to the lecture. I just did so earlier today. I will publish this once I post it on YouTube. I'll publish the link, and we'll be okay with that. Okay. So look for the announcements and we'll get going on it. Thank you.